place added together on that street.
Start a franchise.
That one, I mean, it's
Go
good.
on the ground.
There's Chick-fil-A in 3 places within a mile of center campus. There's one over at the student center, there's one there, there's some.
There's a food truck.
Huh?
There's a food truck.
A Chick-fil-A food truck? I didn't know. All right, now here's the deal. I've been approached by everybody that wants a final on Monday at 10 o'clock. Is that all right with you? Then based on this being a reading, and we'll do it right here. Now, I'm gonna check with my boss and make sure we can do it, and I'll send you a message, all right? Or I'll post something on Window. Can you call our buddy and make sure that he's okay with it?
Trent?
Mm-hmm.
Yes, sir.
You don't have to do it right now, but I mean, call and let me know.
Okay, I'll call
So
you.
that's cool with me. I'll make it fun. And it was scheduled for
Wednesday at 4.
Alright, so if I get shot down by my boss or something like that, then we'll do it Wednesday at 4. Alright? Cause I gotta make sure that it's done in accordance to, and nobody's complaining about this, right? Alright. Oh, for the record, final, probably 6 or 7 pages. That means a different theme on each page.
Yeah.
And then, there might be like 2 or 3 parts to each. For instance, if you're doing traveling wave thing, I might ask for the electric field, then the average power density. And things like this, if you have a Friis transmission equation or something like this, or a radar, I might ask for the power density at the actual target, power density at the return to the radar, then the amount of power received by the radar, things like that. You know, so it's always pertinent to the problem, but in a different aspect, something different. All right, so now, for that, I'm gonna also give you some formulas. For the antennas, I'll give you the gain for the half wave, or you gotta know the short for yourself. Half wave, yeah, it's just sine squared theta for power pattern.
Yeah.
Times 1.5. I'll give you for the half wave dipole. I'll give you I think that's really the only thing we're using.
We really only did like halfway and short.
Yeah, but I mean, for anything else, I'm thinking about it, the general Friis equation, I'm not gonna give you, you're gonna have to know that, you're gonna have to know radar equation, radar range equation, and
I know there was on that one quiz we took, you gave us the
wire diameters for EMC.
yeah, there's that, but
I'll give you any,
like the curls and stuff.
I can give that to you. I'll give you the back, yeah, the curls, divergence, stuff in different coordinate systems,
Yeah.
Laplace integrated. Yeah, that's fine. Provide that. You pretty much know what's going to be on the final. I'm going to think about plane waves, plane wave power density, reflections, then shields, where go through a shield, right? That's one. Then you have waveguides, how a waveguide looks like a transmission line. Remember we did those problems?
Yeah.
How it looks like a transmission line, and how to get the power, wavelength in the guide, things like that, velocity, or phase velocity, group velocity in the guide. I'm not going to ask you anything about fiber optics. I'm going to ask you about, this is for, in general, for radar, the range equation, a Doppler shift, things related to radar in general, power density on the target. What else? I'm just going through my mind all the things that. I mean, I can see this kind of thing happening when I take a waveguide. Say I take a voltage source into a waveguide, and then attach the waveguide to an antenna, something like that. I'm not sure what I'm going to do, but that's at least a feasible problem. The next thing after that, when we have radar range equation, Friis transmission equation, Propagation through a lossy media, remember, as you go through the lossy media decays. Then we have EMC, what a resistor, capacitor, inductor look like, right? And how when the frequency, what frequency you have, these things start not looking like what they're meant to be. And then remember, there's usually the resonant frequency is the key thing to find, and then there's that low cutoff frequency for each element. Then we had EMC, where we had the actual square wave source, and we had two break frequencies. One is 1 over pi tau, and the other is 1 over pi tau rise. And you had to be able to find out the voltage using the approximate method at the load for any kind of filter. Y'all remember doing that class? So that one's going to be. Then, common mode chokes. You have to know about that. That's fairly straightforward. The stuff, it's really going to be impedance matching with elements using LNet network. So this is microwave for microwave. S parameters to, you have to,
Do we need to bring the Smith chart?
Yeah, why don't you bring your own, all right? That because you can print them out to your spec. You want to enlarge them, you can do that however you want them. The rotated Smith chart. Nobody's in here, is there? Are they? I got people looking at that door at me. No, they're probably taking a tour. I'm going to give you an S parameter one for sure, so just be aware of that. Like the S parameter problems I was doing. All right. Y'all remember those? We can do one of them too.
You're talking about with the EMI, right?
That's chapter 10, not EMI. S parameters were S11, S2. S11,
okay.
S21, S12, and S22, remember that? And
two-port network stuff?
Yeah, two-port networks. I'm not gonna ask anything about couplers. Anything specific about it. But if I give you a typical kind of problem, I expect you know how to do it. And that's really about it. That's about all we've done in a nutshell. It doesn't seem like that much, but that's chapter 6 on to the end of the book, 6 through 10. And I can think of, I look at these things and I can come up with all sorts of crazy problems. But you can pretty much predict them. You've got all the homework. Do you want me to work any problems specifically before I go? Yeah.
Can you put the test tube solved on the
what?
On the OneNote?
Test tube.
Yeah. Can you send me an email? Remind me, I'll do that so I don't forget. I'll be happy to. It isn't up right now?
Not that I see.
Tell you what, I'll do it as we're talking. Does anybody have any other problems they'd like to see?
Do S parameter problem?
Yeah, I will. If you got one in mind, let me know. If not, I'm sure I can. It's really, calculating the S parameters.
I think choosing out that would be.
I want to put that test up now while I'm talking. Make sure it's not a problem. Is it supposed to rain this weekend or not?
Really don't know. Wouldn't surprise me if it is.
This is Alabama. Not this weekend?
No.
Good. Think.
That's what the weatherman said.
Last weekend said it was gonna rain the whole weekend, it didn't.
It says partly cloudy. That's it.
How can you lose with that forecast? Okay, can you see if it's there? I think it is. Which S parameter problem?
10.25 looks alright.
10.25.
Yeah.
Go ahead.
It says cut a 50 ohm transmission line and insert a series 50 ohm resistor followed by a shunt 50 ohm resistor.
And?
And then that's the network, and it wants the scattering matrix, if it's lossless, if it's reciprocal, and then also the insertion loss.
Alright, so when you're doing this network business, this is gonna be port 1, this is port 2. This would be V1 coming in this way. This would be V1 coming out this way. This would be, well, incoming would be V2 plus, outgoing would be V2 minus. And the equation is V1 minus, V2 minus, equal to S11, S12, S21, S22 times V2 or V1 incoming V2 incoming or V2 plus. That's the general form. For S parameters. Then, for the specifics on this one, if we look at this right here, we see that if I look at port 1, from port 1 side, I have a 50 ohm line here. It comes in, and then it's going to hit 50 ohms of resistance here. But now I have 50 in parallel 50, so this is going to be 25, right? 25 ohms?
Yeah.
Right? And now I can say really the reflection coefficient here would be V1 minus over V1 plus, assuming that V2 plus is 0, right? So in this case, it is going to be 0 because this is Z0, it goes into a matched load here. Everybody got that, class? So it's into a matched load. That means my input impedance right here is 75 ohms. Agree with me there? And now I can say that now this looks like the classic, the reflection coefficient at 1 is S11, and that's just equal to Z load, or 75 minus 50 over 75 plus 50, right? So that's going to be 25 over 125, right? And that's going to be 1/5. You all agree with me there, class? Right? It's the impedance you're going into, which is 75, minus the impedance you came from, which is 50, right? Over the sum of the two. Everybody got that? So that's going to be S11. Now S21 is equal to V2 minus over V1 plus. This is the forward gain, by the way. All right, now with this one, when I take a look at what happens here, I have to take a look at first the transmission coefficient. This is my actual device right here, right? That I boxed. Do you agree with me, class? So when I take a look at what V2 minus is, V2 minus, what's coming out? First, it would be V1 plus. Then it would be times the transmission coefficient, right? And the transmission coefficient at port 1 is equal to 1 plus the reflection coefficient. Does everybody agree with me there, class? Transmission is 1 plus reflection, correct? That means here, I've got 1/5 plus 1 is 1.25. Now that's the voltage just on the inside of this, correct? Right there, right? The transmission when I take the transmission coefficient, multiply it by V1, now I have the voltage on the inside of this transmission line, right, or this S parameter device, correct, class?
Yeah.
Now I have to do voltage division right here. So now that voltage, V1 prime, call it V1 plus prime, is going to be multiplied by, well, here I got 50 in parallel with 50, so it's going to be 25, right? Over 25 plus 50 or 75. So that means I've got really 5/4 is 1.25 times 1/3 would be equal to my V2 minus times V1 prime part. V1 plus. Do you agree with me, class? Everybody?
Oh, there should be 1.2 instead of
Or
1.5.
Sorry.
Just 1 plus 1/5.
Yes, you're right. Absolutely.
So
My
it's
bad.
6/5.
Pardon?
Yeah, you would change it.
Call it 1.2, right?
Yeah.
Everybody agree with us? Agree? Now, if we have that, this times 1/3, and that means S21 is equal to simply 1.2 times 1/3 or 0.4. Is that right, class?
Yeah, it's 2/5.
All right, so this is my S matrix so far. I have 1/5, and then 0.4 here, or now I'm going to erase this right here. After that, now I get S22, and how do I get S22? You tell me now. What is it really? S22 is what? V2 plus, or I mean V2 minus over V2 plus, right? With V1 plus being set equal to 0, which means it's matched, and that's a matched system there. Do you agree with me, class? All right, so what is that? Well, that's really what? The reflection coefficient looking into this system, correct? And if you look at this, I've got, what I have is 50 ohms here in series with 50 ohms, so that's 100 ohms, right? It's really going to be 50, and that's a 50 ohm line. And then here I have 50 ohms as well. And then I have transmission line. I have Z naught equal 50. And what I want is the actual reflection coefficient of port 2. Agree, class? Because that 50 is in shunt with it. So that means I've got 100 in parallel with 50. Do you follow me? Isn't that right? This is 50 in series with 50 is 100, and it's in parallel with 50, right? 100 in parallel with 50. So that's going to be, I'll just call that, this would be reflection coefficient. Well, let's call this Zn right here. And that would be 100 in parallel 50. And it's coming from an impedance of Z naught equals 50 ohms. So 100 in parallel with 50 is like 1 in parallel with 2 or 2/3, correct?
Yeah.
It's gonna be
2/3.
2/3 of 50, which is number. What is that? It's gonna be 50 times 10 squared over
It's like
150, right? So
33.
33.333 ohms, right?
Yeah.
So that's just 33. And that makes the reflection coefficient here equal to 33.333 minus 50 over, and this would be 83.333. And that's negative what? That's negative 24.6666 over 83.33. What is it?
Minus 0.2.
Again, minus 0.2, surprise. So we've got, this one is minus 0.2. Oh, sorry, not that one, this one. Right there, because that's reflection coefficient. Now for the reverse transmission coefficient, how do we get it? S2 or S12 is equal to what? V1 minus over V2 plus, so it's the reverse gain, correct class? Alright, so now I look in here, I mean, I've got the reflection coefficient at port 2 right here, right? Now I can get the reverse transmission, right? Coefficient is 1 plus that, so I can say tau 2 would be equal to 1 minus 0.2 or 0.8 would be the transmission coefficient. And that means this, when V2 is coming in this way, I have to multiply it by the transmission coefficient first. And I can say V1 minus is going to be V2 plus, then it's times the transmission coefficient, and that's how much voltage will be here, right? And that's 50, it's going to be divided across 50 in series with 50, right, class? Y'all see that? So it's going to be 50 over 100 or 1/2, right? So it's that times 1/2. And now you get what? Over V2 plus, which means tau is equal to 0.8 times 1/2. And that will be S21, and that's really 0.4, correct, class? So this is 0.4. Agreed? This is actually 0.2 as well. Agreed? So now they want to know if it's reciprocal, right?
If it's lossless, if it's reciprocal, and the insertion loss.
All right. We can get the return loss too. So, if it's reciprocal, it means what? The S conjugate will be the same thing as S, isn't that right?
Mm-hmm.
Or, I call it con. Yeah, I think they start in the book, I'm not sure the symbol they use. It should say this would be a reciprocal matrix, right?
Yeah.
A reciprocal means you just shift diagonals, these diagonals, correct? So it is reciprocal, do you agree with me?
Yeah.
So check reciprocal. The next thing it asks for if it's lossless, and lossless says what? But if I take S, right, and multiply it by S conjugate transpose, I think in the book, he has that, doesn't he? The conjugate, just look. This is on page 562. Let's see. Looking for,
S transpose times S con
oh, I'm sorry.
equals the.
That's
unity
right.
matrix.
It's gonna be this conjugate times transpose. So the conjugate of the matrix, there's nothing with phase in it. The conjugate is the matrix. Are you with me, class?
Mm-hmm.
I mean, conjugate means you change the phase, so that's the same thing. So that's 0.2 minus 0.2, and then it's 0.4, 0.4. By the way, you can tell it's lossless, lossy by one way. You can just see resistors, right? Anytime you got resistors with current, it's loss. So it's lossy guaranteed. It's gonna be that. And then it's gonna be times the transpose of the matrix. Well, that's gonna be minus that's gonna be 0.2, 0.4, 0.4, minus 0.2. And if that comes out to be just what? 1100, then it is. That's what you did in the book, right? Yeah. And so what does it come out to? What? I got this times this, 0.2 squared plus 0.4 squared. Is that up to 1 or not? If I have this times this, row column, I get 0.2 times 0.2, or 0.2 squared, and I get 0.4 times 0.4, or 0.4 squared, right? What do you get with row column multiplication now?
0.2.
This times this is 0.2?
Yeah. Cause it'll be what, 0.04 plus 0.16? It's 0.2 times 0.2
Yeah,
squared is
and so
0.04.
just looking at that
That's already
means it's
right.
not, right? And you could take one look and see it's lossy,
Yeah.
because it's made of resistors. Whenever you see a resistor in the system, you know it's lossy. It's obvious. Do you have a question? No, okay. Everybody got that?
Yeah. And then the last one was insertion loss.
All right. Now, insertion or really the reflective losses, the actual insertion loss, the forward insertion loss is going to be 20, right? Times the log here of, it's minus 20 actually, of the magnitude of S21. Now that's the loss. So what does that come out to be? S21 is 0.4, correct? So what is 0.4 log of that times minus 20, what do you get?
8.
8 dB?
Yep.
Does he have answers in it?
Yeah, that's all right. We got all right.
Anything else? That's a typical problem. I mean, you can always add something. I mean, I think this is Dr. Gross.
I guess, are you gonna give us one with like any inductors or capacitors in there, or is it?
Possibly, yeah.
Okay,
I mean, I don't know yet, because I frankly haven't had thoughts about making up a problem.
cause that would just add like some phasor.
Yeah, then whenever you have capacitors or inductors for this little network instead of just resistors, then you're going to get a phase, and then the transpose will, or when you conjugate. I mean, when you take the conjugate, then you do have the phase inversion, and that's important. Any other problems? I didn't give you one of those on the test.
No, you didn't give us homework on the dude.
On S parameters?
I don't believe so.
Well, I'm going to give you some.
Okay.
And I'll give you the solutions too. I'm sorry if I didn't.
You didn't give us shielding homework either.
Well, I'll give you both. Alright, can you send me an email, somebody send me an email to post shielding and S parameter homework. Just send me an email,
We can do that.
and I'll do it right after class. I don't know about you, but I'm just ready for a break. I've had a lot to do the last couple of weeks. I still got more. One thing when you get older, you're gonna find out. It doesn't matter if you get all your work done and you're ready to leave. There's always a lawn to mow, I mean, you can hire a couple. There's always things, hedges to trim, something in the house that needs attention. And if you got kids, then the fun never stops. 'Cause they need rods. Anything else? Nothing? Okay. Well, I had fun this semester with you guys. It's a pretty bright class on average. Really good bunch. If you want to see me about something, I don't see a need to keep lingering. But if you want to see me, I'll be upstairs. Otherwise, enjoy yourselves. And I'm going to check with the boss right after I get out here to see if Monday at 10 is allowable. And if it is, I'll send it. How about if I post on OneNote, all right? And just check. As a matter of fact, one or the other, I'll make sure everybody knows. But on Facebook, I think it's easy. And if I can't do it, I can't. But I can. I've never moved a final exam before.
Note for your.
I know you want to write it. You just keep it then. Is that all right? Move to take your final your test score.
Yeah, I assume 10 a.m.
Because honestly, I can give you a test, but
It's 2 so.
Real last question. We never, we turned in like a MATLAB project, and you never returned
I got
it
that
or
upstairs.
anything.
It's either at home or upstairs. Do you,
Okay.
do you need that?
No, it's just, I don't know what, I guess
I
we
think
don't know what we made, how
I
it
think
like
everybody's
affects our
probably got a
grade.
pen on that. I
Okay.
mean, if you turn it in, unless you fouled up something wrong. it'll
Yeah,
get it.
and is that just like an extra quiz grade, or?
Well, what I do
You
is
said
this,
bonus.
I take that as the quiz, but what I do is drop the lowest. So
Okay.
that can replace your lowest quiz,
Okay, cool,
and that's the idea.
Okay.
thank you.
Take care, man.